Warning, the video you're about to watch contains mathematics at the level of integral calculus, also known as Calc 2. All material has an assumed prerequisite of differential calculus and a full semester course in trigonometry. A thorough review of prerequisite topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This video is meant for Calculus 2 students who are going through surface area material involving just standard functions, not parametric functions, but just standard functions. If you don't know what I mean by parametric functions, it's because you haven't gotten there yet. That's fine. All right, so let's go ahead and dive right into this. Determine the surface area of the solid obtained by rotating the given function about the given line. And in this case, the function you're given is y equals x times e to the x. We're doing this from x equals 0 to x equals 1. We're rotating that about the x-axis. And because surface area usually always involves the arc length formula as well, there is a likelihood that you're going to have to use some numerical approximation technique to get an actual answer. Let's showcase this by going ahead and setting this up. First thing I actually want to do is possibly get an idea of what this curve looks like. It's not necessary, but it's nice. When x is 0, well, we can easily see that y would be 0. And when x is 1, we can see that y is going to be 1 times e to the first, or about 2.718, something like that. Now, what I'm about to draw is a very crude approximation of what this curve might look like, but I'm going to say it's probably something like this. And in reality, actually, it's probably a little more steeply sloped right around here. It probably comes in like this, but I'm not too concerned about that right now. Honestly, I'm just getting a rough sketch, and we're going to rotate that about the x-axis, and we want to find the surface area of the resulting solid. So maybe your solid looks something like that. Surface area is something like the volume, right? When you do volumes, you take a vertical slice here, or you would at least in this case, and you'd rotate that vertical slice all the way around to get a disk. But in this case, we don't want the volume, so we're not going to do that. Instead, we're going to paint a little strip that's along the edge of this curve, and we're going to rotate that strip all the way around the outside of this volume. Now, the difference between this drawing that I have here and the previous slice with the disk is that the disk had a horizontal top to it, and it was an approximation of a volume of that slice. In this case, we don't have a horizontal slice. We're just taking a look at this wiggle along the edge, this little arc length, if you will. And we're taking that arc length and we're just shading the region that it cuts out as it rotates around. So we're painting the outside of this slice here. And of course, it does go back behind the screen, but I'm not going to be able to paint that very well with the colors that I have. So I'll just leave it like this. Now, when you're painting the outside of an object like this and you're taking a circular strip, well, the surface area of that ith strip there is going to be the circumference of that ith strip times the thickness of that ith strip. And the thickness of that ith strip is just the wiggle there, the ds that we have. Technically, it would be ds sub I because it's the ith strip. We happen to know for a circular object, the circumference is 2 pi times the radius to the center of axis of rotation. That would be visually the following. That distance right there is the radius to the central axis of rotation. It need not be the x-axis. It could be y equals a -1 or y equals a -10 or something like that. Or technically, I suppose you could wrap it around x equals 2 or something like that. It doesn't really matter. The mechanics are essentially the same. You have a circumference, 2 pi r sub I, times the thickness of that paint strip, which is ds sub I. And now you need to make a choice. are you going to do this with respect to X, or are you going to do this with respect to Y? A lot of people will immediately say it has to be with respect to X because it's a vertical slice, but that is actually not the case. You don't have to do this in terms of X if you don't want to. However, if you want to do this in terms of Y, that means you would have to solve this equation right here for X to find out what X is in terms of Y. The likelihood that you're going to be able to do that is slim to none. Thus, we will go ahead and perform this integration or build this problem in terms of X. We'll do everything in terms of X, which means that the choice for ds here is going to be the square root of 1 plus dy dx squared and then dx. These are technically supposed to be sub-i's here, but that's okay. That's not that big of a deal that I didn't write that in. I'm just giving you the formula right now. The radius of rotation though, well, you can see that distance is a y value. This blue distance right here, well, now that I've done that, it's red, but whatever. That distance is a y value. So let me write that in. And if we're integrating eventually with respect to x, you want to trade that y sub I out for something in terms of x. Luckily, they gave us that y is equal to x times e to the x. So let's go ahead and trade that out right now. Now that we have everything written in terms of x, I'll go ahead and insert that into an integral, and we'll integrate from x equals 0 to x equals 1. And just like we did way back when we were learning arc lengths, we'll go ahead and do some scratch work on the side to set up this radical right here. Now, just to let you know, in this problem, they specifically kind of gave us a big old hint that we are going to need numerical approximation techniques to find this value. So that's great. However, sometimes you won't be given that. Let's say you are working on a textbook that does not give you the hints like this, where they're trying to imply that you need to use a calculator or some type of technology. Well, your best bet is to do as much simplification on the radicand as possible. But once you start working with the integral and trying to integrate it, it should become very obvious after about 2 or 3 minutes of effort that maybe you cannot integrate this, and maybe you should switch to numerical integration techniques. I don't want to convince you to just set yourself that time limit and then immediately switch over to numerical integration techniques. However, to be honest with you, that's probably what most people would do. So let's go ahead and find out what dy dx is. Well, we know that y is x e to the x, so by the product rule, we get that dy dx is e to the x plus x e to the x. Now we want to square that. Actually, what I'm going to do prior to squaring that is I'm going to write this as e to the x times the quantity 1 plus x. That way, when I square it, it's a little bit cleaner. And now we know that when we plug this into the radicand, we'll be adding 1 to that. And to be honest with you, that's not going to clean up at all. So let me plug that in there and just showcase that. And there we go. Now, if you go ahead and try your best to simplify this integrand here and maybe use substitutions or something like that, you're going to find out very quickly that you're going to be stuck in a really vicious cycle. This is a gnarly integral. And so the wonderful hint they gave us, approximate this using the Simpson's rule with 10 slices, we're going to go ahead and pay attention to that and go and set that up right now. When you're running Simpson's rule or any numerical integration technique, you're going to have to list out what n, a, and b are. A is your lower limit of your integration, b is your upper limit of your integration, and n is the number of slices. So let's go ahead and find out what delta x is here. And setting up Simpson's method itself, just to showcase what it looks like, it's going to be delta x over 3, and then we're going to evaluate f at x sub 0 plus 4 f of x sub 1 plus 2 f of x sub 2, and that 4-2 pattern will repeat until you get down to the n minus first term that stops at the 4 times f of x sub 9, and then you add f of x sub 10. Now, what are those f of x subs? Well, we happen to know that x sub I is defined to be a plus I delta x. And a being 0, this is just going to be I times 1 over 10, or I over 10. That'll be very helpful. Going back to our integral here, we're going to say that this is going to approximately, therefore, be s sub 10, Simpson's rule with 10 slices, which we know is equal to, well, we have 2 pi, that's going to be hanging out front, and then we're going to multiply that by delta x over 3, delta x being 1/10, and then multiplying the denominator by 3, we get the 30 downstairs. So I'll just multiply this by 1/30th. And then we will have f of, again, x sub 0 plus 4 f of x sub 1 plus 2 f of x sub 2. And since I already wrote this down, I'm just going to immediately do that right there. And at this point, you can use either Desmos or Excel or Google Sheets, anything you want to go ahead, or just a calculator really, to go ahead and do this. Note that f, the function, is the integrand right here, the entire integrand. It looks pretty messy, but it's not too bad. So let's go ahead and finish out this problem in Desmos. So here we are in Desmos, and I'm actually not going to go to the graphing calculator. I'm going to go to the scientific calculator. It's a little bit easier to do this in the scientific calculator, in my opinion. That's just an opinion though. So now I'm going to seed the function. Our function was x e to the x square root of 1 plus e to the 2x times 1 plus x being squared. And that being our function, we can go ahead and start with our 2 pi over 30, which I could do a little bit of math for Desmos here and just call that pi over 15. And now I'm going to go ahead and in this group, just do f of x sub 0. Now I'm typing that in just to showcase kind of my mindset, plus 4 f of x sub 1 and so on and so forth. Remember, x sub I is defined to be, at least in our case, I over 10. So x sub 0 is 0 over 10. X sub 1 is 1 over 10. X sub 2 is 2/10, and so on and so forth down the line. Now I'm just going to pause here for a moment so you can see, once I get to f of 0.9, which is x sub 9, I have 4 times f of x sub 9, or f of 0.9. Now I'm going to go ahead and end with plus f of 1. And you can see right here, the approximation for the surface area is going to be 24.1458. And they didn't really specify how many decimal places they wanted in this problem. So I'm going to go actually just state it to the fourth decimal place here. So 24.1458. Now, just for giggles, let's take a look at actually what Desmos would compute the value to be. So I'm going to type int for integral. And we're integrating from 0 to 1 of 2 pi x e to the x square root of 1 plus e to the 2x times quantity 1 plus x being squared dx. And you see the integral that Desmos computes is 24.1443. If I round to the same 4 decimal places, how far are we off? Well, 24.1458. We're off a little bit, probably 1/1000th, somewhere in there. So it's not too terrible, but it also wasn't a ton of work. We would not be able to compute this integral by hand, so it's good to have Simpson's rule to help us do the numerical integration. All right, so I hope this is a good reminder of numerical approximation techniques using Simpson's rule, and also how to find the surface area of a revolved volume. I hope to see you in another video. Take care.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close. Don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.